Durango, Colorado, late September 1865. Across the settlement, families raced to complete their cabin fireplaces before winter's arrival. But one man, Henrik Larsson, a stonemason from Norway, was just breaking ground on his construction. Neighbors watched with growing concern as Larsson positioned his fireplace at a sharp diagonal, cutting across the corner instead of mounting it flat against a wall. The design looked wrong. It seemed to defy common sense, using far more materials than a typical fireplace. Larsson's approach required nearly 35% additional stone, with massive extensions reaching deep into both adjoining walls. John Mitchell, known throughout the area as a skilled carpenter, couldn't understand what he was seeing. "A fireplace belongs flush against the wall," he muttered, "not suspended in midair like an unfinished mistake." Robert Carson, respected across multiple counties for his masonry expertise, wrote off the entire project as foreign foolishness that wouldn't survive a real Colorado winter. Then the cold descended. January 18, 1866, brought temperatures of negative 22 degrees, and they remained there for over 3 weeks. The brutal freeze would ultimately take 27 lives throughout the region. Conventional fireplaces couldn't cope. Desperate families began burning their furniture just to stay warm. Mitchell's household burned through 2.5 cords of wood in 9 days and still struggled to maintain warmth. Meanwhile, Larsson's unusual corner-positioned fireplace kept his home at a comfortable 71 degrees while using only 45% as much firewood as his neighbors needed. The massive stone structure continued radiating heat for over 14 hours after the flames went out. What ancient principles had this Norwegian craftsman brought from Scandinavia that experienced American builders had never learned? If you appreciate these accounts of forgotten wisdom that proved itself through time, consider subscribing. There are more remarkable stories worth preserving. Henrik Larsson worked in the September chill, his rope stretched tight between 2 walls, meeting at a right angle. The hemp line created a diagonal across the corner space, marking a location where conventional builders would never consider construction. John Mitchell paused his own work, splitting roof shingles, drawn by curiosity toward Larsson's bizarre project. "That's the strangest approach I've witnessed, Henrik," Mitchell called out, though the air was cool enough to see his breath. "A fireplace sits against the wall or fits into the corner proper, not floating in empty space." Mitchell had constructed cabins throughout Colorado and Wyoming for over 8 years. Never had he seen someone position a fireplace to touch 2 walls while truly belonging to neither. Larsson kept his focus on the measurements, his hands bearing scars from 13 years of working Norwegian stone. He adjusted his rope until it divided the corner perfectly. "In Bergen, we designed for warmth, not appearances," he answered, his Norwegian accent thick. "Stone retains the fire's heat long past when the flames die. A corner provides 2 walls for storing that warmth rather than just one." Mitchell shook his head and went back to his shingles. Nearby, Franz Hoffmann glanced up from laying his own foundation. The German settler had overheard the exchange and found himself recalling something his grandfather once mentioned about Bavarian heating methods. But Hoffmann stayed quiet. On the frontier, wisdom meant sticking with proven American techniques, not gambling with unfamiliar foreign concepts that might endanger a family when winter came. Late September brought Robert Carson, the area's established mason who'd built chimneys throughout 3 counties since 1861. Carson showed up at Larson's site with his professional tools, level and square in hand, instruments that had earned him recognition as the authority on proper stonework. What he found troubled him deeply. The Norwegian had dug a foundation stretching 20 inches into each wall, forming an enormous stone base that seemed to devour precious cabin space. The firebox would face toward the room's center at 25 degrees, an orientation Carson had never encountered in 4 years of regional work. Most concerning was the sheer quantity of stone involved, over 300 pounds of local sandstone, costing Larson roughly 35% more in both materials and effort compared to a standard wall design. The man squandering near 35% extra stone and positioning that firebox where it's useless for heating. Carson complained to Mitchell and Hoffman that evening. Norwegian ways don't suit Colorado winters. I've constructed 58 fireplaces in this territory, and each one sits properly against a wall where it should be. Larson pressed forward despite the community's doubts. Every morning, he and his teenage son Eric gathered sandstone from the creek, selecting pieces for their heat retention qualities rather than the limestone most builders used. Norwegian tradition required specific stone characteristics, density, structure, and thermal properties that Eric was learning to recognize by feel and weight. While neighbors completed their fireplaces in 4 days following standard patterns, Larson devoted 3 full weeks to carefully angling each stone for the precise geometry his design demanded. "Why are we building this way, Father?" Eric asked as they positioned the angled firebox walls. Born in Colorado but raised on Norwegian building knowledge, the boy understood both American frontier skepticism and Scandinavian engineering principles. Larson indicated the stone mass extending into the cabin's corner walls. "Notice where the fire will sit. As it burns, heat strikes both wall masses simultaneously. A standard fireplace warms one wall inadequately and loses most heat up the chimney. Our method stores warmth in 3,800 pounds of stone, then releases it gradually throughout the night." He gestured with his hands, demonstrating how radiant heat would bounce off the angled firebox into the living space while also warming the thermal masses built into both corner walls. As early October arrived, established builders grew louder in their criticism. Mitchell calculated that Larson's excessive stonework had stolen 3.5 weeks he could have spent gathering firewood or preparing other winter necessities. Hoffman questioned whether the angled design might cause dangerous draft issues that would fill the cabin with smoke. Carson proclaimed the whole endeavor a waste of quality stone that would fail when genuine cold arrived. Yet the mathematical precision of Larson's work suggested something different. His firebox opening measured exactly 34 inches wide by 26 inches high, angled to direct 68% of radiant heat into the living area, versus the 42% achieved by wall-mounted designs. The thermal mass reached precisely 20 inches into each adjacent wall, creating a heat storage system capable of retaining warmth equivalent to 3 hours of active burning. The chimney drew with 18% superior efficiency, thanks to the corner position's natural airflow benefits, ensuring cleaner combustion and lower wood use. October 22, 1865, Larson finished his fireplace, while neighbors completed their standard wall designs. Light snow began that evening, gentle flakes promising the season ahead. John Mitchell visited Larson's cabin to inspect the completed work. Despite his reservations, Mitchell felt curious about the Norwegian mason's unconventional approach. The firebox's angled opening seemed to aim directly at the room's center rather than heating one wall primarily. Stone masses extended visibly into both corner walls, creating what appeared to be integrated heat reservoirs. "I still think you've used too much stone, Henrik," Mitchell admitted, running his hand along the smooth sandstone surface. "But I'll grant it solid work. We'll discover come January whether all that extra effort was worthwhile." Early winter brought moderate cold that both standard and Norwegian designs handled adequately. Larsson's fireplace demonstrated slightly superior performance, maintaining warmth with noticeably less wood than Mitchell's conventional system needed. But the real difference wasn't dramatic enough to silence skeptics who continued viewing the corner design as an expensive mistake. Late December, weather turned colder, bringing temperatures into the low teens that stressed standard fireplaces throughout the settlement. Mitchell found himself feeding his fire constantly, burning wood faster than he'd anticipated. Hoffman experienced similar challenges, his German timber frame design struggling to retain heat as outside temperatures dropped. Yet Larsson's cabin remained consistently warm, the massive stone structure absorbing heat during active burning and radiating it for hours afterward. Then, January 18th arrived with catastrophic cold. -22 degrees descended on Durango, and the temperature refused to rise. Day after day, the brutal freeze persisted. 21 consecutive days of life-threatening cold that pushed standard heating systems beyond their capabilities. Mitchell's family huddled near their fireplace, burning furniture when firewood supplies ran dangerously low. 2.5 cords of wood disappeared in just 9 days, yet their cabin barely reached survivable temperatures. Hoffman's household faced identical struggles, burning everything combustible to maintain minimal warmth. Throughout the settlement, families fought desperately against the cold. Carson's professional masonry work proved inadequate, as his own fireplace consumed enormous wood quantities while failing to heat his home properly. Children slept in multiple layers near dying fires. Adults debated whether to risk traveling to relatives in warmer locations or endure the freeze. Across 3 counties, the killing cold was claiming victims. 27 people would ultimately die during those 21 days, most from hypothermia in homes with inadequate heating. Inside Larsson's cabin, conditions told a dramatically different story. His corner fireplace maintained 71 degrees while burning only 45% of the firewood Mitchell's household consumed. The massive sandstone structure had become a thermal battery, absorbing heat during active burning and releasing it gradually for 14 hours after flames subsided. Eric Larsson could touch the stone walls hours after the fire died and still feel significant warmth. The Norwegian design's efficiency meant the family had ample firewood reserves while neighbors exhausted their supplies. By day 13 of the freeze, Mitchell appeared at Larsson's door. "Henrik, I need to understand what you've built here," Mitchell said, his pride clearly damaged. "My family is burning through everything we have, and your cabin stays comfortable. What makes your fireplace work so differently?" Larsson invited Mitchell inside, explaining the principles behind Norwegian thermal engineering. The corner position allowed heat to radiate into both adjacent walls simultaneously, rather than heating a single wall inefficiently. The massive stone quantity created thermal mass that absorbed heat during burning and released it slowly over many hours. The angled firebox reflected radiant heat into the living space instead of sending it primarily up the chimney. The specific stone selection, sandstone rather than limestone, provided superior heat retention properties. In Norway, fuel is scarce and expensive, Larsen explained. Norwegian masons learned centuries ago how to store warmth in stone. We build for survival, not convenience. Mitchell studied the construction carefully, finally understanding what he'd dismissed as wasteful. The 35% extra stone wasn't excess. It was essential thermal storage. The corner position wasn't poor planning. It was strategic heat distribution. The extended construction time wasn't inefficiency. It was precision engineering. Word spread through the frozen settlement about Larsen's remarkable fireplace. Families facing dangerous cold visited to see the Norwegian design in operation. Hoffman arrived with detailed questions about stone selection and thermal mass calculations. Carson came reluctantly, his professional certainty shaken by the crisis. "I've constructed dozens of fireplaces across 3 counties," Carson admitted, examining Larsen's work. "But I never understood heat storage like this. I was building for appearance and following standard patterns. You built for function and survival." As the freeze continued into its 3rd week, the performance gap between heating systems became impossible to ignore. Larsen's cabin remained comfortable while surrounding homes barely maintained survivable temperatures despite burning multiple times more fuel. The mathematical advantage was undeniable. Norwegian thermal engineering had proven itself under the most extreme conditions Colorado could deliver. When the cold finally broke in early February, the settlement took stock of the disaster. 27 deaths across 3 counties. Hundreds of families had exhausted fuel supplies and burned furniture, tools, even structural timbers to survive. Economic losses were devastating, but one Norwegian immigrant's strange corner fireplace had kept his family safe and comfortable throughout the entire crisis. John Mitchell approached Larsen the day after temperatures rose above freezing. "Henrik, I was wrong about your fireplace," Mitchell said directly. "I need you to rebuild mine following your Norwegian design. Whatever it costs, whatever time it requires, I won't risk another winter with standard construction." Hoffman made a similar request, acknowledging that his German timber framing techniques needed to incorporate Norwegian thermal principles. Robert Carson's conversion was perhaps most significant. The region's expert mason publicly admitted that 4 years of professional experience had taught him appearance over function. "Every fireplace I build from now on follows Henrik's principles," Carson announced. "I won't be responsible for family freezing because I was too proud to learn from Norwegian knowledge." Throughout spring 1866, Larsen became the settlement's most sought-after builder. Families who'd survived the freeze with standard fireplaces wanted Norwegian designs before the next winter. Neighbors who'd mocked the corner position now requested exact replicas of Larsen's construction. The Norwegian mason's calendar filled with projects throughout Durango and surrounding settlements. Mitchell's reconstruction began in late March. Larsen supervised the demolition of Mitchell's standard fireplace, explaining why the original design had failed so dramatically. The wall-mounted position provided minimal thermal storage. The single-wall heating created uneven temperature distribution. The firebox angle sent most heat directly up the chimney rather than into living space. The limestone construction absorbed and released heat poorly compared to sandstone. Your old fireplace was built following frontier patterns that worked adequately in mild winters, Larson explained. But those patterns never anticipated sustained extreme cold. Norwegian designs assume the worst weather and engineer for survival in those conditions. Mitchell's new fireplace took 4 weeks to complete, following precise Norwegian specifications. Corner positioning at exactly 48 degrees to both walls. Thermal mass extending 20 inches into each adjacent wall. Over 3,800 pounds of carefully selected sandstone. Firebox angled to reflect maximum radiant heat into the living area. Chimney positioned to optimize draft efficiency. Hoffman's project incorporated hybrid elements, combining German timber framing with Norwegian thermal engineering. The result integrated Larson's stone selection and thermal mass principles, while maintaining some traditional German structural techniques Hoffman valued. The combination created a heating system superior to Hoffman's original design while preserving elements of his cultural building heritage. Robert Carson's professional transformation proved most dramatic. The master mason spent weeks studying with Larson, learning Norwegian principles that contradicted much of his established practice. Carson questioned everything about his previous work, recognizing that professional success had been based on appearance and reputation rather than genuine heating performance. "I thought expertise meant following proven patterns," Carson reflected. "Henrik showed me that real expertise means understanding why those patterns work or fail. Norwegian masons know stone and heat in ways I never imagined." By summer 1896, 19 cabins within 50 miles incorporated Norwegian corner fireplaces, with construction requests arriving from settlements Larson had never visited. The technique spread through Scandinavian immigrant networks extending across Rocky Mountain communities in Wyoming, Montana, and New Mexico. Larson's cousin Anders, settled near Santa Fe, received detailed plans and material specifications, beginning the Norwegian fireplace migration through mountain regions where heating efficiency meant survival. Durango Settlement Council officially recognized Larson in April, appointing him to oversee all future fireplace construction in the region. The position acknowledged that his Norwegian methods had prevented multiple deaths during the January crisis. Larson would now inspect and approve fireplace designs before construction began, ensuring families wouldn't face another winter with inadequate heating systems. His first official project involved redesigning the settlement's planned community building, replacing the architect's standard central fireplace with 2 angled corner units capable of heating the larger space efficiently. Wood dealers reported significant changes in fuel consumption patterns by summer 1867. Firewood sales to Durango area settlements had dropped 32% compared to pre-Norwegian averages, representing thousands of cords families no longer needed for winter survival. The economic impact extended beyond individual savings. Reduced fuel demand lowered regional wood prices while freeing timber for construction projects previously delayed by heating fuel requirements. Larson's documentation practices, learned through Norwegian tradition, preserved construction details, proving invaluable to future generations. His son Eric maintained detailed records of fireplace specifications, thermal performance measurements, and fuel consumption data, creating an engineering database tracking Norwegian heating methods under Colorado frontier conditions. The records included stone selection criteria, mortar mix ratios adapted to Colorado clay deposits, and seasonal performance comparisons demonstrating consistent superiority over standard frontier designs. Winter 1867 or 1868 provided additional testing as temperatures dropped to -15 degrees for extended periods. Larson's Norwegian designs handled these conditions without difficulty, while standard fireplaces throughout the region struggled to maintain life-sustaining heat. Regional building costs dropped $12 to $28 per cabin, as Norwegian thermal efficiency reduced firewood preparation requirements and eliminated emergency heating modifications frontier families had previously considered essential. The savings represented significant economic relief for settlers operating on subsistence budgets, allowing families to invest resources in livestock, land improvements, and agricultural expansion rather than excessive fuel preparation. Modern thermal engineering research conducted by the Rocky Mountain Heritage Foundation in 1976 confirmed Larson's empirical results through controlled testing of reconstructed Norwegian fireplace designs. Foundation researchers built replica Larson fireplaces using original specifications and materials, measuring thermal performance against period-standard heating systems under laboratory conditions. The testing documented 2.6 times greater heating efficiency, consistent temperature advantages of 16 to 20 degrees, and heat retention equivalent to 9 to 13 hours of active fire. Results validated Norwegian engineering principles through contemporary scientific methods. Archaeological evidence preserved at Larson's original Durango site provides physical documentation of Norwegian construction techniques adapted to Colorado frontier conditions. The Colorado Historical Society maintains the original cabin and fireplace where visitors can examine Larson's mason marks carved into sandstone blocks. Thermal mass integration extending precisely 20 inches into corner walls and firebox angles demonstrating mathematical precision achieved through traditional craftsmanship. The site represents one of few intact examples of Norwegian thermal engineering applied to American frontier architecture. Contemporary passive solar and earth-sheltered home construction employs thermal mass principles identical to those Larson applied in 1865. Positioning heat sources at angles maximizing thermal storage while minimizing fuel consumption. Modern heating engineers recognize Norwegian building techniques as sophisticated thermal engineering, achieving energy efficiency through traditional knowledge rather than technological innovation. Larson's primitive corner fireplace anticipated by over a century the energy-conscious building methods contemporary builders consider advanced environmental design. The ultimate vindication of Larson's Norwegian techniques came through survival statistics, demonstrating the life-saving value of traditional knowledge applied to frontier conditions. Winter 1865 to 1866 killed 27 people across 3 Colorado counties due to inadequate heating. Thermal engineering analysis suggests Norwegian fireplace designs, had they been widely adopted, could have prevented 75% of those deaths through superior heat retention and fuel efficiency. Larson's strange corner fireplace hadn't just challenged frontier building assumptions. It proved that dismissing traditional knowledge as primitive often reveals not their ignorance, but ours.